Hello friends, welcome to YouTube channel Electronics. In this video, we will learn RC low pass filter. The electronic filter is a circuit used to selectively pass or reject certain frequency components of an electrical signal. They are designed to remove unwanted frequency components and enhance the desired ones. So now based on the frequency band which is being passed by the filter, the filters can be broadly classified into four primary types: low pass, high pass, band pass and band reject filters. We will briefly discuss them one by one. The first one, low pass filter. This low pass filter passes the low frequency signal starting from 0 Hz up to cutoff frequency and rejects all frequencies beyond this cutoff frequency. Here, by observing the frequency spectrum of an ideal low pass filter, we can understand that up to 0 to 20 Hz frequency, this filter passes all signals and rejects all signals above 20 Hz frequency. So now the second type of filter is the high pass filter. A high pass filter allows signals with frequencies above a certain cutoff frequency and rejects signals with frequencies lower than cutoff frequency. The frequency response of an ideal high pass filter looks like this. Here in this case, the cutoff frequency is 30 kHz. So this high pass filter rejects all frequencies below 30 kHz and pass all frequency signals above 30 kHz. Next, the third type of filter is band pass filter. A band pass filter passes frequencies within a specific range or band and rejects or blocks frequency signals outside that range or band. The ideal band pass filter frequency spectrum looks like this. It has two cutoff frequencies, FC and FC'. Here in this case, it is 20 kHz and 40 kHz. So this filter passes all frequency signals between 20 kHz to 40 kHz and rejects all signals below 20 kHz as well as above 40 kHz. Now the fourth type of filter is band reject filter. A band reject filter rejects a specific range or band of frequencies and passes all frequency signals above or below that range. The ideal band reject filter frequency response looks like this. Here also we have two cutoff frequencies, FC and FC'. So this band reject filter passes all frequency signals below cutoff frequency FC, that is 20 kHz, and also passes all frequency signals above cutoff frequency FC', that is 40 kHz, but rejects all frequency signals between these cutoff frequencies FC 20 kHz and FC' 40 kHz. Band reject filter works quite opposite to band pass filter. So here in this video we will discuss on low pass filter. This low pass filter can be further classified into two types. The first one, active low pass filter, and the second one is passive low pass filter. This classification is simply based on the components that are used to design the filter circuit. If the filter circuit is designed by using the active components like op-amp and transistor, then such filters are known as the active low pass filters. On the other hand, if the filter circuits are designed using passive components like resistors, capacitors and inductors, then such filters are known as passive low pass filters. So the advantage of using active filter is that it also provides gain to the input signal, while in case of passive low pass filter, the output is always less than the input signal. The passive low pass filter are mainly three types: RC low pass filter, RL low pass filter and RLC low pass filter. In this video, we will particularly learn about the RC low pass filter. As the name indicates, RC, it is made by connecting resistor and capacitor in series. The input signal is applied across the resistor and capacitor, while the low frequency output is taken across the capacitor. Now let's understand how this circuit works as a low pass filter. If we see over here, these resistor and capacitor are connected in series. As we know that the capacitive reactance can be denoted with Xc. So the total resistance of this circuit RT equals to R plus Xc. We are applying input voltage Vin here. So the current I can be given as Vin divided by by R plus Xc. We are taking output voltage Vout here. It is nothing but voltage drop across this capacitor. So Vout can be given as I into Xc. Here I can be written as Vin divided by R plus Xc. So Vout can be rewritten as Xc divided by R plus Xc into Vin. And we know that Xc equals to 1 by 2 pi Fc. So Xc is inversely proportional to frequency. So as the frequency of the input signal increases, the reactance of this capacitor will decreases and vice versa. So if we apply input signal here, because of low capacitive reactance for the higher frequency signals, all the high frequency components will bypass through this capacitor to the ground. Hence Vout is 0 for high frequency signal. While the higher capacitive reactance for the low frequency signals, the low frequency components of the input signal cannot pass through this capacitor. Hence will appear across the output terminal. So we can say Vout is maximum or Vout equals to Vin for low frequency signal. In this way, this series RC circuit acts as a low pass filter. So it passes the low frequency components in the input signal and rejects or attenuates the high frequency components in input signal. The frequency response of an ideal low pass filter looks like this. In this case, 30 Hz is the cutoff frequency. So it passes the signals below 30 Hz frequency and rejects all frequencies above 30 Hz. But the actual response of a low pass filter looks like this. So at low frequencies, low pass filter provides 0 or minimum attenuation, but as the frequency increases, the attenuation will also increase, and the frequency at which the output is 0.707 times of the input signal. That frequency is known as the cutoff frequency or minus 3 dB frequency. So at this frequency, the output will be 1 by root 2 times of the maximum value of the output value, and after this cutoff frequency, the output value will reduce at the rate of minus 20 dB per decade. That means if you increase the frequency 10 times, the output will reduce by a factor of 10. Hence this cutoff frequency Fc can be given as 1 by 2 pi Rc. So now let's derive this cutoff frequency expression. So earlier we have seen that Vout equals to Xc divided by R plus Xc into Vin, and if you only consider the magnitude, then mod of Vout equals to mod of Xc divided by mod of R plus Xc into Vin. Now if we take this Vin on left hand side, then mod of Vout by Vin equals to mod of Xc divided by whole root of R square plus Xc square. Here we know that Xc equals to 1 by 2 pi Fc. That can be written as 1 by omega c. Now as we know that at the cutoff frequency, the output will be 1 by root 2 times of the input. That means the gain or attenuation of this circuit will be 1 by root 2. So 1 by root 2 equals to 1 by omega c divided by whole root of R square plus 1 by omega c whole square. And if we square on both sides, then we will get 1 by 2 equals to 1 by omega c square divided by R square plus 1 by omega c whole square. If we further simplify this equation, then we will get omega equals to 1 by Rc, or we can say that cutoff frequency Fc equals to 1 by 2 pi Rc. So in Rc low pass filter, as we increase the input frequency, the output signal's amplitude will reduce. Not only the amplitude, but also phase of the output signal will also get changed, and this phase change can be expressed as phi equals to minus tan inverse omega Cr. So now if omega equals to 0, then the phase value pi equals to minus tan inverse into 0, that equals to 0 degree. So at omega equals to 0, then the output will be in phase with the input signal. Now at cutoff frequency omega c, as we know that omega equals to 1 by RC. So the phase value will be minus tan inverse into 1. That equals to minus 45 degrees. So at cutoff frequency, the output will be 45 degrees out of phase with the input signal. And if omega equals to infinity, then pi equals to minus tan inverse into infinity. That equals to minus 90 degrees. So now if we plot the phase versus frequency curve, it will looks like this. At 0 frequency, the input and output phase difference will be 0. And at cutoff frequency, the phase difference of input and output will be minus 45 degrees. That means output signal lags the input signal by 45 degrees. As the input frequency increases more than the cutoff frequency, the phase difference will also increases to the minus 90 degrees. This is how frequency and phase response will looks like for low pass filters. Now let's solve this example based on low pass filter. In this example, we have been asked to find out minus 3 dB or cutoff frequency for the given low pass filter, and we have also to find out the output voltage at applied input signal of 12 volts and 3 kHz frequency. First, to find out the cutoff frequency, we use this equation. Fc equals to 1 by 2 pi RC. Here, as we know that pi equals to 3.14, R equals to 1 kilo ohm, C equals to 0.1 microfarad, and we will insert these values in this formula. So Fc equals to 1 divided by 2 into 3.14 into 10 to the power of 3 into 0.1 into 10 to the power of minus 6. If we simplify this, we get Fc equals to 1 divided by 6.28 into 10 to the power of minus 4. That equals to 1592 Hz or 1.592 kHz as cutoff frequency of this low pass filter circuit. So now we need to find Vout at input voltage of 12 volts and 3 kHz frequency. Here, to find out Vout, we must use this equation. Vout equals to mod of Xc divided by whole root of R square plus Xc square into Vin. So first of all, we need to find out the value of Xc at 2 kHz frequency. As we know that Xc is equal to 1 by 2 pi Fc. We will insert respective values in this equation. That equals to 1 divided by 2 into 3.14 into 3 into 10 to the power of 3 into 0.1 into 10 to the power of minus 6. If we simplify this equation, Xc equals to 1 divided by 18.84 into 10 to the power of minus 4. That gives Xc value as 531. Now we will insert Xc value in Vout equation. So Vout equals to 531 divided by whole root of 1000 square plus 531 square into 12. That gives Vout as 5.63 volts. So we get 5.63 volts sine wave as output. If we plot the frequency response of this low pass filter circuit, then it will looks like this. Here the cutoff frequency of the low pass filter is 1.592 kHz. The 3 kHz frequency will be around here. So at this frequency, we have found that the output value as 5.63 volts. Suppose if you want to design a low pass filter so that this 3 kHz signal should be attenuated as much as possible, then we must design higher order filters, and as we go for the higher order filters, the slope of this curve will increase gradually and the amplitude of Vout will reduce accordingly. So in this way, using higher order filters, we can achieve the much sharper roll off. Let's say if you are using the second order filter, then the slope of the curve will be minus 40 dB per decade. So if you are designing the nth order filter, then the slope of the curve will decay minus 20 n dB per decade. That means if you are designing fourth order filter, then the roll off will be minus 80 dB per decade. And these higher order filters can be designed by cascading the first order low pass filters. So now let's see how the second order low pass filter works. Here we have cascaded two first order low pass filters. Let's assume that the cutoff frequency of the first filter is Fc1 and the cutoff frequency of the second filter is FC2. So the total cutoff frequency of the second order filter can be given as FC equals to 1 by 2 pi whole root of R1 C1 R2 C2. If you use the same value resistors and capacitors for both these filters, that means R1 equals to R2 and C1 equals to C2, then the cutoff frequency FC becomes 1 by 2 pi R1 C1. So now as we go for the higher order filters, the attenuation at the cutoff frequency will also increases. So for the first order filters, as we have seen that at the cutoff frequency, the output Vout equals to 1 by root 2 times of input Vin. Now here for the second order filter, the output Vout equals to 1 by root 2 into 1 by root 2 into Vin. That means the output Vout equals to half of the input. Here if we cascade n number of filters with the same cutoff frequency, then for the nth order filter, the output will becomes 1 by root 2 whole power of n into Vin. It means output will be reduced more. So in this way we can get sharp and sharp roll off. But designing the higher order filter is very complicated. It is because if we are designing second order low pass filter by cascading two first order low pass filters, we must be sure that the second stage low pass filter should not get overloaded by the first stage. And to minimize this loading effect, we should choose the values of the second stage low pass filter, resistor R2 and capacitor C2 in such a way that the loading effect of the first stage will be minimized. To minimize the loading effect, the value of R2 must be at least 10 times of the R1. And the best way to minimize the loading effect is to use the active filter, because active filters not only provides the gain but they also acts as a buffer between the two stages. We will discuss active filters in upcoming videos. That's all about RC low pass filter. If you have learned from this video, please do mention them in the comment section below. Thanks for watching. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe and turn on notifications for more such videos. Have a nice day.